In today's lecture, we will go through the acidic character of alcohols and phenols. When we talk about acidic character of alcohols and phenols, we know by basic definition that any compound that releases hydrogen ions in water is acidic in nature, right? So that means if you add alcohol or phenol to water, it will release hydrogen ions, due to which it shows acidic character, right? And like we used to do in basic chemistry, when HCl is added to water, right, it will furnish hydrogen ions, right? And it is due to these hydrogen ions that your HCl is acidic, right? More is the number of hydrogen ions, more is your acidic character, and less is the number of hydrogen ions, less would be the acidic character, right? And more hydrogen ions would be in the forward direction, right? So anything that favors the forward reaction will increase the acidic character of the compound. Anything that favors the backward reaction will favor the less acidity of the compound, right? Anything that favors the backward reaction will decrease the acidity of the compound, right? So what could be here that will decrease the acidic character, right? If you look at this simple reaction, if you remember, we used to do acidic character is a weak acid, acidic acid is a weak acid, right? Because when you add it to water, it will produce acetate ions, right? Acetate ions which reacts with hydrogen ions, and they will give you back acetic acid, due to which this is a weak acid. Whereas HCl is your stronger acid. Why? Because it is almost completely dissociated in water, right? And it furnishes more hydrogen ions, so forward reaction is favored. Whereas if we look at this, your acetate ions, right, are less stable, due to which they immediately react with hydrogen ions to give you back acetic acid, right? Something similar will happen here in case of alcohols and phenols, right? And some experiments were carried out on phenol. Phenol will turn blue litmus paper red, right? And if, like we used to do with acids react with sodium metal to give you sodium chloride plus hydrogen gas, right? Similarly, phenol also gives hydrogen gas with acids, right? And it turns blue litmus paper red. It turns blue litmus red, right? And it produces hydrogen gas, phenol. It produces hydrogen gas with sodium metal, right? And it neutralizes, phenol neutralizes your sodium hydroxide base, like hydrochloric acid neutralizes sodium hydroxide to produce sodium chloride. Similarly, your phenol will also react with sodium hydroxide to give you sodium phenolate, right, which is a neutral compound, right? So these 3 points shows that phenols are acidic in character. Whereas if we talk about ethanol, which is an alcohol, it does not turn blue litmus red, right? That means it is not acidic, right? But we say that when your alcohol is added to water, it will form your ethoxide ion and hydrogen ions, right? It will form ethoxide ion and hydrogen ions. That means, since it does not turn blue litmus red, that means this forward reaction is not favored, right? Due to something, these two react and gives you back ethanol, right? Due to which it is very less acidic actually, right? It is very less acidic to the extent that it does not turn blue litmus red. Right, now let's look into the reason why phenols are more acidic compared to alcohols, right? If you add phenol to water, it will form this ion, sodium phenoxide, right? It will form sodium phenoxide plus hydrogen ions, right? Due to these hydrogen ions, phenol is acidic, right? Now since it is more acidic, that means in this case this forward reaction, that means reaction in the direction where you have hydrogen ions is favored, right? And how is it favored? That means these two are not reacting, right, immediately to give you phenol back. Why? Because this is more stable, right? This is more stable and this is less stable, right? So the stability of phenoxide ion actually makes phenol more acidic compared to ethanol. Now if we talk about ethanol, this ethoxide ion has a formal negative charge, right? And it immediately reacts with hydrogen ion to give you back ethanol, right, which is a neutral compound, right? That is why it shows less acidic character. Why? Because you have less hydrogen ions, because this ethoxide ion reacts with hydrogen ion, right, and give you back your ethanol. But you have negative ion, negative charge here also, that can react with hydrogen ions to give you back phenol. But this is not happening here, but it is happening here, right? So due to something, this phenoxide is more stable. Let's see why phenoxide is more stable. Since we know about the chemistry of phenol, this phenol has two lone pair of electrons. Now this lone pair of electrons can enter into conjugation with the benzene ring, right? Since it can enter into conjugation with the benzene ring, it adds to the stability, right? It adds to this. These lone pair of electrons can enter into conjugation with the benzene ring, due to which it is resonance stabilized, right? Since it enters into resonance with the benzene ring, it is resonance stabilized. Phenol is resonance stabilized. Similarly, if you look at this phenoxide ion, on phenoxide ion also you have these lone pair of electrons that can enter into resonance or conjugation with the benzene ring, right? That adds to the stability of this phenoxide ion. That means this phenoxide ion is also stable due to resonance, right? But as this forward reaction is favored, that means this is more stable than this, right? This phenoxide is more stable than your phenol, right? Let's look into the reason. To find why phenoxide is more stable than phenol, we need to look into the various resonance structures of phenol and phenoxide, right? This is your phenol, right? It will enter into conjugation with the benzene ring, right? So since it enters into conjugation with the benzene ring, you have now positive charge on this oxygen atom, right? The other lone pair enters into conjugation with the benzene ring. It enters into benzene ring basically, right? So here you have this, right? Now this will here, right? This will move like this, right? Since this electron pair is moving, actually this is what these arrows are showing, right? Here, negative charge here. So these are various resonance forms of phenol. Now let's look into the resonance forms of phenoxide. This is for phenol, right? Resonance forms. Now let's look into resonance forms of phenoxide. Right, this is your phenoxide, right, where this lone pair of electron will again enter into benzene ring. It enters into resonance with the benzene ring. So what we are drawing is various resonance forms of phenoxide ion. Right, so here right, right, since now this negative ion will again move similarly as in your phenol, right, producing various resonance forms, right. So this will also move in the same way, like this, right. This is the negative charge, right. Now it will also move like this, double bond, right. Come here. So these are resonance structures of phenoxide and these are resonance structures of phenol, right. What you need to understand here is that this phenoxide is more stable, right, due to which you have more hydrogen ions. It is stable, that is why it does not immediately react with hydrogen ions to give you back phenol. Why it is more stable? These resonance structures will tell us, right. If you look at these three resonance structures, let's say this is second, this is third, and this is fourth, right, and this is your fifth, this is your sixth, and this is your seventh. Resonance structures second to third have positive charge as well as negative charge, right. It has charge separation that will make it less stable, right. Whereas if you look at phenoxide, you don't have charge separation in these three forms from fifth to seventh, right. Since you do not have charge separation, you only have this one negative charge on all these three forms. This adds to the stability, right, of this phenoxide ion. So let's write it like this, that phenol, the resonance forms of phenol second to fourth have charge separation. This is your positive charge, this is your negative charge, this is your positive charge, now negative charge has come here, this is your positive charge, now negative charge has come here, right. So you have charge separation here that reduces the stability of the phenol, right. Basically charge separation reduces the stability of phenol, right. Whereas in phenoxide, no charge separation, have only single charge, right, that is negative charge, right. I hope till this point it is clear. Since you have only negative charge, this is more stable than this. That means this phenoxide is now more stable than this phenol, right. Now since this is more stable, right, than this, so we know that every system will try to achieve stability. That means now this phenol will ionizes to give you phenoxide ion, right, along with hydrogen ions, right. That means the forward reaction is favored because of the more stability of phenoxide ion, right, due to this reason. So you have more hydrogen ions in this direction, right. In the forward direction you have more hydrogen ions. That is why your phenol is more acidic, right, than ethanol. Now if you look at ethanol, right, this ethoxide ion it has no resonance forms, right? It has no resonance forms and it has a negative charge, and you have a positive hydrogen ion which will immediately react to give you back the ethanol, which is neutral, right? So acidic character, which is due to hydrogen ions, right, is reduced because these hydrogen ions will immediately combine with ethoxide ion, because ethoxide ion is less stable, right? So these less stable ethoxide ion will immediately react with hydrogen ions to give you ethanol, right? So your ethoxide ion is less stable, right? Because it has no resonance forms like phenoxide and phenol. It's less stable and combine with hydrogen ions to give ethanol, right? So backward reaction is mainly favored here. That is why ethanol is very less acidic compared to phenol, right? I hope this is clear why phenol is more acidic than ethanol, right? Because of the resonance stabilization of phenoxide ion. Phenol and phenoxide ion, both these are resonance stabilized, and phenoxide is more resonance stabilized. That is why your forward reaction is favored, right? And you have more hydrogen ions in forward direction, due to which this is more acidic. Whereas if you look at ethanol, ethoxide ion has no resonance forms. This is not resonance stabilized, neither ethanol nor ethoxide, right? So this will combine with hydrogen ion to give you back ethanol. So no hydrogen ions, right? Or very less hydrogen ions, which means less acidic, right? I hope this is clear. Thanks.